So now we compare differences in proportions. Okay. So in the previous example, we compared differences in sample average, which were measured as game rounds played, okay, between gate at level 30 versus gate at level 40, okay. But now we are going to look at proportions, and the proportions is just a number between 0 and 1. Okay, so it's like a probability. And we have a question. Do the data show that the level 30 version produces a higher proportion of users who return to the app 7 days after installation? Okay, and this is our kind of research question. So then we have to look at the hypothesis, and we have, like, this is the retention rate, okay, the gamer retention rate, and we want this to be higher, okay. So if we change the game, will the retention rate go up? So if we change then we follow the alternative hypothesis. So is the difference between proportion for gamers who use game at gate with gate at level 30 higher than the proportion of users coming back to the game when the gate is at level 40? Okay, so this is, if this is true, then action. Okay, and if this is true, no action. Okay, so P30 is proportion of users in gate level 30 who return 7 days after installation, okay? And P40 is the proportion of users in gate level 40 version who return 7 days after installation, okay? So then we can use the data from the experiment to compare the proportions, okay? So now we can use a two-sample z-test. We're not using the t-test because, as we saw earlier, the difference in mean is normally distributed. So we can use a z-test and the z-table, which is normally distributed, okay? So the two-sample z statistic is just the sample. This P1 hat is the sample proportion from population 1 minus the sample proportion from population 2 minus a certain cutoff, okay, divided by the standard error of the sample proportion from sample 1 or population 1 minus the sample proportion from population 2, okay. So this is just a number. This is just a number. And we have to check that the sample size condition is satisfied in both groups, okay? In both groups. So for the first group, we take the sample size times the proportion, okay? or the sample proportion. Okay, and what does this mean? It means that you actually get the number of hits, right? Equal number, just a second. Number of hits, okay? And this is the number of misses. Okay, so what we can see is that we have to have a certain distribution between hits and misses to be able to use this inference model. Okay, so what we can do is that you have the population parameters, which are P1 and P2, and as usual, you are not observing these population parameters. So, but the hypothesis says something about the population parameters, the unobservable population parameters. So the alternative hypothesis is that the proportion is higher for the version after an action than the proportion with no action. Okay, and this difference should be greater than a cutoff. Okay, and this cutoff is based on profitability. So if it costs you anything to sorry, to implement the change, then this cutoff should take that into consideration. Okay. But what you can observe is this. I'm just drawing some glasses here. So these P1 hat and P2 hat, these are the sample proportions. These you can actually observe because you can just look at your data, and if the specific data rows contain 1, then it's a hit. If they contain 0, they are a miss. Okay. And so these sample statistics, these sample proportions, they are just number of hits divided by n. Okay, for group 1, and for example. Okay. And here you can make calculate the standard error of this difference, which is just the sample proportion for group 1 times 1 minus sample proportion for group 1, which is just the sample probability of a hit times the sample probability of a miss divided by the sample size for that group. This is the variance, okay, the sample variance of the proportion, and you do the same for group 2. And this estimated standard error you can use to make these z statistic, which is just the difference in proportions minus a cutoff divided by the standard error of the difference. And you reject the h naught of no difference if the p-value is less than the significance level, or if the z statistic is greater than the critical value. Okay, and remember that the z statistic just measures this difference in proportions as measured in number of standard deviations. Okay, so it really says how many standard deviations away from 0, or our cutoff, is our difference in proportions as measured in standard deviations. Okay, so let's look at cookie cats, and we have the same samples which we use, and we have the gamers at level 30. They are 44,700, and the proportion of those who downloaded and installed this game version 30, of all of those, 19.02% return after 7 days. Okay, so the retention rate is 0.1902, and this is higher than those who are exposed to or use the game level 40. They have the same sample size as previously, but here only 18.2% return 7 days after installing the game. So they have a retention rate of 0.182. Okay, so we see that this is higher than this. Okay, so if we change the gate to level 30, we think that a higher percentage will return to the game 7 days after installation. Okay, but is this difference significant? And we have to look into that. So, does the A/B test show that moving the first gate to level 30 increases the proportion of users who come back to the game 7 days after installation? So that's our research question. Okay, use 1% significance level for the hypothesis test. Okay, so we should be quite certain that this is true before we make a change. Okay, hence the quite low significance level. So what we do is just like previously, we have to formulate our hypothesis. Okay, so we start with the alternative hypothesis, and what would make us change from level 40 to level 30. Okay, well, if the proportion at 30 is higher than the proportion at 40, then we are inclined to change the game. Okay, so if the retention rate for gate at level 30 is higher, then we want the higher retention rate. Okay, because that's what makes us money. And the alternative hypothesis, the null hypothesis, is thus everything else. Okay, which means that this difference is less than or equal to 0. Okay, so that's the first step. Okay, so the second step is to calculate the z-stat, okay? And we know the z-stat, it's the sample proportion, the difference, and we do not have a cutoff, so we set the cutoff to 0 because we are just interested in, is it bigger than, is P30 bigger than P40? And we don't need a margin, okay? And we divide by the standard error of this sample difference, okay? And this sample difference is just, let's see, it's P30, so let's see, we can just take this and SE P30 hat minus P40 hat. It's really just the square root of P30 times 1 minus P30 hat, okay, divided by N30. And this is really the proportion standard, or no, the proportion variance, okay, for this P30 proportion, okay. So, and we have to add these proportions, or these variances. So we do the same for the proportion variance for gate at level 40. Such. And if you just think about it, then P30 hat is just the probability we found that gamers come back after 7 days when gate is at 30, and 1 minus P30 hat is the opposite. It's the probability that they don't come back, okay? So divided by the sample size, okay? So this is just the standard error, okay? So if we plug in, then we have P30 is or P30 hat, I have to say, is 0.1902, okay? So 0.1902 minus the P40 hat, which is 0.1820, okay? 0.1820. That's the difference, okay? And the standard error, we have the function up here, the equation. So this will give us, let's see, just give us some space, 0.1902 times 1 minus 0.1902. I will definitely run out of real estate here, divided by the sample size, which is 44,700. Okay, and we have to add the other variance, okay, which is 0.1820 0.20 times 1 minus 0.1820, okay, divided by 45,589, and we take the square root of that, okay? So, okay. We do this. It's okay. And this is going to be 3.165, okay? So that's the z value that we got. So what does this mean? This means that this difference in player retention rate is 3.165 standard deviations away from 0. Okay? And already we know that this is significant. But how do we know that? Well, then we just look at the critical value. Let's see, we can do this. Okay, so we have 3 critical value. So what we know is that the normal distribution is as such, and it's centered at 0, and the value over here, or the area over here, should be 1%. Okay, 1%. And what we can do is that we can look at the z table here, and this is the z value. It's the number of standard deviations away from the center, from 0, and we are looking at a one-sided test, right? We want the area under the curve for a one-sided test. So then we look at the z value, and our z value was 3.165, as you remember. So we go down here and we find that we have this value, and our z value is higher than this, but not as high as this z value, okay? So a conservative value would be to take the lower value here, and we see that it gives us we want to look at the area under the curve, or the C value, the critical C value, which gives us 1% area under the tail, right? So what we have to do then is to look at this column. We want the probability, or the area under the curve, to be less than 0.01, or 1%. So we go down here and look for 0.01, and we get a critical value of 2.3263, okay? So we go back and find the value here was 2.326, okay? So this is our critical value. So then we have to test. So is our Z value greater than the critical value? Okay, and we have our Z value is 3.165, which is greater than the critical value of 2.326, right? Which implies we reject H naught, okay? And keep the alternative hypothesis of P30 higher than P40, okay? So we reject H naught. And now for the p-value, okay? What is the p-value of the test from part E, okay? Which means that then we have to take the Z statistic that we got, and we have to compare it with what kind of area under the curve will we get if we go 3.165 standard errors away from the mean, okay, away from 0. And now we look at this number down here, which is a bit lower than our Z statistic, and this number is a bit higher than our Z statistic. So for example here, if we I can't write on this one, so we take this one as a conservative measure, and we get a p-value of 0.001, which means that the p-value is 0.1%, right? So from the Z table and Z statistic, we get P equals to 0.001. Okay, and this is lower than the significance level of 0.01, which is 1%. Okay, so how can we interpret the results from part F? Okay, well, if we want to look at part F, what is the p-value of the test from part E, then the probability of getting a Z statistic which is greater than 3.165 is or more is 0.1%. Okay, so if H naught of no difference is true, then our result is very unlikely. Okay, and we have here, well, actually we can write it, interpret the results from part F is that let's say let's say the probability getting a z value, just remember that the z value is really the difference in proportions as measured in standard errors, okay? The probability of getting a z value greater than 3.165 or more, greater than 3.165 is 0.001 or 0.1%, assuming H0 is true. Okay, now it's written. Okay, so to point H, the hypothesis test in part E requires that sample size conditions hold. Is this the case? Well, we saw that there has to be 10 misses and 10 hits in each sample. Okay, so the condition is really n, which is sample size. Let's see. Here we go. N times the p hat 1 has to be greater than or equal to 10, and n 1 times 1 minus the probability of a hit has to be greater than or equal to 10. Okay? Or we can say 30 here. Okay, so and P30 hat is just the probability of hitting. 1 minus P30 hat is just the probability of not hitting, the probability of a miss. And if we put some numbers in for level 30, then we have 44,700, which is N30, times 0.1902 is greater than 10. Okay, we see that immediately. And the sample size, 44,700 times 1 minus 0.1902 is greater than or equal to 10. So this is okay for those in group with gate at level 30, right? What about level 40? And the sample size is 45,589 times 0.1802, which was the probability or the proportion of a hit with the gate at level 40. And you see that this is greater than or equal to 10, okay? And likewise, the sample size times the probability, the sample probability of a miss to 0, it should be. ØAMET2200. Okay. Damn it. Is greater than 10. So you see that the sample sizes are okay. So see you next time.